Again, with this problem, we have an absolutely brutal region of integration that would just be horrendous. I've graphed it here, and I stole my graph from Desmos, but I can show it to you in Desmos. And again, it just took a lot to be able to show this region. It took several different sections, actually 3 different sections of graphing, so it would take 3 separate triple integrals to be able to find this, which is just awful. So we need to transform this. All right, so let's look at the equations that we have here. We have x equals y squared, and we have x equals y squared minus 4, which I thought I'll go back to the Desmos so you guys can see. So x equals y squared is this green one right here, and x equals y squared minus 4 is this red one right here. And then 9 minus y squared is this one, and 16 minus y squared is that one. So you can see the 4 different colors there. All right, so that'll help us with our labeling. So I'm going to go back and I'm going to label those graphs right here. There they are. So I've got all of them labeled. So this is this one, and so on. Okay, and just as we did in the previous one, we're going to kind of put these together. So we notice that these two both have a y squared in common. So that's what we're going to use. But we're going to solve it kind of for the numbers. So we could say x take away y squared is negative 4. But I don't really like that negative number in there. I'd rather have it be positive. So if I bring the 4 over and subtract the x, it'd be y squared minus x equals 4. And then this one, if I bring the x over, it'd be y squared minus x equals 0 because there's nothing left over there. All right, so that's going to help us out because now that means that we know what we're going to do. We're going to set u equal to this thing that keeps showing up. U is y squared minus 2x. Excuse me, y squared minus x. I don't know where the 2 came from in my head. All right, y squared minus x. There we go. There's our u. Now let's look at it. What we're going is from u equals 0 to u equals 4. This will be great. This will give us nice, easy limits of integration. Lovely. All right, let's do the same for these two. So this is 9 minus y squared equals x. So if I bring the y squared over, that would be y squared plus x equals 9. And then y squared plus x equals 16. So now we're going to set v equal to this y squared plus x. And then we know we're going from v equals 9 to v equals 16. We have a super easy area of integration. We're only going to 4 here for the u because this is the u axis. So u equals 0 to u equals 4. And we're going from 9 to 16. I'm going to make this a little taller here. It's still not to scale, I grant you, but I'm just trying to give a sense of this. So 9 and 16. So we have this rectangle, not drawn to scale, but bear with me here. And this is our new region. So region R, the region of integration that was given, is over here. So this is R, this is S, the new region. And we like it because, boy, does it have a lot easier numbers to work with. We're going from 9 to 16 for our V's, and we're going from 0 to 4 for our U's. So far, so good. So which way are we going to integrate with? We're actually going to do dv du, or excuse me, du dv. We're going to go horizontal this one time. Not for any particular reason, but this 0 right here is mighty tempting. I'd rather integrate with the 0 first because that'll make something go away, right? As opposed to the 9 and 16, which are both numbers. So I'm just thinking ahead that the integral will be easier if I go du dv, right? And it's because of the 0. In the previous example, there was no choice because it was all 4 of them numbers, so it didn't really make any difference. So because of u equals 0, we'll make things easier. We'll do that one first for the integral, right? For the integration. Okay, but we're not there yet, not by a long shot. We still have to come up with the transformation and the Jacobian, and that's actually going to be dicey in this particular example. Okay, so the transformation, t. The transformation, we're going to take our equations that we have set up for u and v, and we're going to solve them. So let me write them again. If u is y squared minus x and v is y squared plus x, then if I add them up, I don't need to multiply by anything on this one because the x's will already cancel. So I'll get u plus v equals 2y squared. So then y squared is a half of u plus v. So let me write this. A half u plus a half v equals y squared. So y is the square root of 1/2 u plus 1/2 v. All right, now we're going to do it again. Let's think here. U equals y squared minus x. V equals y squared plus x. Now I've already done the bit where I add them up, so that's no good. So what I'm going to do is I'm going to multiply each one of them by a negative. That'll make the y squareds cancel. Okay, so if I do that, I'll end up with u minus v equals, and then these are going to go away, right? So I made the x's disappear on the first one, so I've got to make the y's disappear on this one. And then I'll have negative x minus x, which is minus 2x. So then I'm going to multiply by a negative 1/2. So I'll get negative 1/2 u plus 1/2 v equals x. All right, I have my x and I have my y. I'm actually going to rewrite y because I have to take the derivative of this, so I'm just thinking ahead. That's 1/2 u plus 1/2 v to the 1/2 power. All right, now the Jacobian. I am running low on space, so let me try to find it right here. So the Jacobian is xu, xv, yu, yv. And you might already realize why we're in a little bit of trouble here, because this is not going to be easy to find. That would be equal to, okay, the derivative of x with respect to u is a negative 1/2. The derivative of x with respect to v is a positive 1/2. So far, so good. But the derivative of y with respect to u would be 1/2 comes down, then this whole thing to the negative 1/2 times the derivative of the interior, which is a half. So it's 1/2, 1/2 u plus 1/2 v to the negative 1/2 times the derivative of the interior, which is a 1/2. I'm going to have to move this over. Otherwise, these are not going to be lined up at all. All right, so this is 1/2 over here. And then the next one will be the same thing, right? It'll be, and you'll notice this is a quarter, right? So a half on the front, right? Because you bring the 1/2 power down, and then you do all of this stuff, and then you multiply again by a half in the middle. Let's save some space here, and let's make it a quarter. 1/4. Because we're going to have to do it again, because the next one's basically the same thing. In fact, it's exactly the same thing. So 1/4 times 1/2 plus, or 1/2 u plus 1/2 v to the negative 1/2. And then we get to multiply. So negative 1/2 times this would be negative 1/8 times 1/2 u plus 1/2 v to the negative 1/2 power minus, and then another 1/8, because a half times a fourth is an eighth, same thing. All right, a negative 1/8 and a negative 1/8, they're like terms. A negative 1/8 and another 1/8 makes negative 2/8. Negative 2/8 is negative 1/4. So it's negative 1/4 times this thing, 1/2 u plus 1/2 v to the negative 1/2 power. There's your Jacobian. All right, so now that we have that all figured out, as ugly as that is, let's actually do the double integral. Okay, so the double integral of y squared dA over region R is going to transform to a completely different integral. Okay, so let's see here. We know we want u to go from 0 to 4. And we know we want v to go from 9 to 16. Let me do it right here. 9 and 16. Then our integral was y squared. Y was this bad boy right here, right? So we're going to take that and we're going to square it. But if you square this, you square square root, you just get the thing, right? So it's 1/2 u plus 1/2 v, right? So there's your y squared. Now you need your Jacobian, right? The absolute value of your Jacobian. Okay, so if I take the absolute value of this, the negative 1/4 will become positive 1/4. And it's just going to go out in front. I'm just going to stick a 1/4 out there, right? And then my Jacobian is everything else that's left. So 1/2 u plus 1/2 v to the negative 1/2. And then I'm going to have du dv. Because u involves 0, that'll be a little easier to do. So there we go. Now, before you panic, notice these two are the same, but they're to different powers. This is 1/2 u plus 1/2 v to the 1 power. This is 1/2 u plus 1/2 v to the negative 1/2 power. So when you have, let me remind you, when you have a to the x times a to the y, that's a to the x plus y. So you can just add those powers, right? And 1 plus a negative 1/2 is a 1/2. So this is really 1/4 and then I'm going to integrate from 9 to 16. Then I'm going to integrate from 0 to 4. And then this whole thing becomes 1/2 u plus 1/2 v to the 1/2 power. du dv. Now I know what you're thinking. You're thinking, oh, we're going to go to Maple. Yes, we are, but not right now. We can do this. We can do this because this is an old-timey substitution. We're going to let w, can't use the letter u because u is already used up. So we're going to let w equal 1/2 u plus 1/2 v. Then I want to take the derivative with respect to u. So the derivative of w with respect to u would be 1/2. So dw, if you will, equals 1/2 du. I'm going to do a substitution. Old school substitution. All right, so this is 1/4 integral from 9 to 16. Then this is w to the 1/2 power. And then instead of du, I'm going to write 2 dw. Let me put it that way. So 2 dw. And then I have another integral which I haven't done. So I have to put this other integral in here, sorry, from 0 to 4, because I haven't done it yet. Oh, it's not 0 to 4 though. Oh, right. I can't put 0 and 4 in because 0 and 4 were u values, and this is no longer u. This is some other thing, w. So I'm just going to leave an integral symbol in there, but I'm not actually going to write numbers. The numbers for v haven't changed, so those are staying 9 and 16 because I'm not messing with those. Okay, so then the integral of this, right, would be, we'd bring the 2 out, so it'd be 2/4 out in front, which I know is a 1/2, but bear with me here. And the integral of this would be w to the 3/2 times 2/3. Then I'm going to integrate this from 9 to 16. And then this is going from some number to some number that I never found, dv. So I'm going to put back in what w was, right? So it's going to come back. So this is going to be 1/3 in front, right? Because 2 times 2 is 4, 4 divided by 4 is gone. And then integral from 9 to 16. And then I have w, which was 1/2 u plus 1/2 v. I'll make that orange just to make that clear. So it's going to be 1/2 u plus 1/2 v back in to the 3/2. And I'm going to take that from, now I can put the numbers in, right? For w, I didn't have them, but now when I put u in, I have u. U is 0 and u is 4. This is why we did the u first, dv. So 0 is really easy. 4 is not too bad either. 1/2 times 4 is 2. All right, so let's put it all together. This is now the integral 1/3 integral from 9 to 16, 2 plus 1/2 v to the 3/2, take away 0 plus 1/2 v, so that's just 1/2 v to the 3/2 dv. And at this stage, we make Maple do it. So let me go grab my Maple. Poof. Isn't that awful? Okay, so just so you can see it, this is the original transformation that I made. And instead of putting the 1/4 out in front, I actually have it down here. So that's where it is. That's the Jacobian, right? The absolute value of the Jacobian. It's not negative because we always take the absolute value. So there's the original. It's just god awful. So then we tell it to do it numerically, and it gives us this, right? So which is great. And then this is the last integral I just had. And then there it is in a numeric form. And sure enough, every time it's 18.786. We don't use Maple for much in this section because most of it is really just graphing in Desmos and thinking about things. I mean, you could graph in Maple as well, but I graphed in Desmos instead. I did that because I can shade in Desmos. It's a lot harder to shade in Maple for a 2D graph like that. So anyway, there you have it. We have transformed and did a pretty tricky Jacobian in this one, as well as a tricky W substitution along the way, which is always a little bit of work.